can you see my screen? So it's a markdown file that I adapted from the bookdown file.
Yes.
Is it visible?
We can see the file, not the knitted document.
Yes, that's exactly what I want you guys to see. That's where I feel like it's easiest for me to be able to manipulate tables and see things. Okay.
No problem.
So it sounds good. Yeah, so today we're working on chapter 12, and it's all about data tidying. And I love this quote in the introduction that, it's from Tolstoy. It says, happy families are all alike. Every unhappy family is unhappy in its own way. And then Hadley's quote that says, tidy data sets are all alike, but every messy data set is messy in its own way. And just a little anecdote, when I first started working, like one of my first analyses where I do a lot of gene expression, in different, so you have like patient samples and then all of the genes in rows. And I was like, these spreadsheets always look exactly the same. And it was a total revelation to me, because normally I work with my own Excels, and then colleagues have their own ways of setting up things. And so to me, it just sort of brought home the idea that yes, there is a good standardized way, and then you can just build off of that when everything is uniform. So we'll be working today with tidyr. It's a package that provides a bunch of tools to help tidy up the messy data sets. And tidyr is a member of the Cohort tidyverse. So I've already loaded up and libraryed it. Okay, so you can represent obviously data, the same underlying data, in multiple ways, right? And so we're going to look at 4 examples as to how the same data is organized in different ways. So table 1. This is just data on countries, years, cases of tuberculosis, and then population, right? So this is table 1. You have countries, then the years, you have 1999 and 2000, then the number of cases of tuberculosis, and then the population for the country, right? So this is the same data, it's just organized differently. So here you have a type column that contains both cases and populations, and then the number of TB cases and the population are represented in this other column called count. Then this table has computed the rate of tuberculosis cases, right? And so here you have TB cases over the population, but this is its own separate column, and it's actually 2 values in that column. And then this table, table 4a, just has cases listed by year, right? So in the year 1999, these are the number of cases for each country, and in 2000, the same thing. And then table 4b has the population for those countries. So it's like the data has been split into 2 smaller data frames, right? So these, although these are all underlying or representations of the same underlying data, they are not as easy to use, and we're going to see why, right? So the idea here is that a data set that is tidy is much easier to work with. And so let's see what tidy data is first. So these 3 rules essentially make a data set tidy, right? All of your variables, like for example, the country, year, cases, population, are in columns. Then your observations, right? So like we had Afghanistan in the year, let's look at table 1 actually. Afghanistan this year, number of cases and population are all in rows, right? And then the values are at the intersection of it. And so you have all of these values listed for each of your different variables. Okay. So let's look back at our 3 or 4 tables, right? So this is table 1, that's table 2, then 3, 4a, and 4b, right? So out of all of these, and you guys, I guess, know the answer already, but only table 1 is tidy, right? So it's the only representation, as we went over it, where each column is a variable, right? And so the question then is, why do you want your data to be tidy, right? And there's many good reasons. These are two. One, it's one consistent way of storing data, right? So if you have a consistent data structure, it's much easier to learn the tools that work with it, right? Because of this underlying uniformity. And then the other thing is that when you have your variables and columns, it really allows R's vectorized nature to shine. So most built-in R functions work with vectors of values, right? Everything nicely stacked in columns. And that makes, transforming or any sort of manipulation that you have to do much easier to do. So for example, dplyr, ggplot that we've seen before, and all the other packages in the tidyverse are designed to work with data in these structures, right? So we'll go over this example of what we want to produce, working with these sorts of tables, and then we'll go over exactly what's happening. Let me run this. Okay, so, why can't I see that? Sorry. Okay, there we go. So essentially what we want to produce at the very end, right, is a table that shows you for each year, like the number of cases for each of the countries, right? And this is just like a basic plot. And what we've done here is essentially computed a new column, right, based off the cases and population that is called the rate of TB cases. And it is just the cases divided by population for every, 10,000 people, right? And so you can see that using table 1, right, which has everything already in its proper columns, then it's an easy thing to do. You just mutate, meaning you create this new column, which is just these other two columns, and some mathematical computation applied to them. So let me see. Okay, so yeah, we'll go over all of this in more detail in the exercises. So okay, so the first exercise is we want to compute the same quantity, this rate, for table 2 and table 4A and 4B, right? And so we're going to need to perform 4 operations. We need to extract the number of TB cases per country per year, then extract the matching population per country per year, divide cases by population and multiply by 1,000, and then store them all back in the appropriate place to get one final data frame from which we can actually graph, right? So let's see. Let's go over this code. Just as a reminder, table 2, right, is the one that has this type column with cases and population all in it. And so what we want to do is make a new table, or called table 2 just cases, right? And then we're going to use filter table 2. We're going to filter by type, just grabbing the cases, right? We need to rename the count column cases in the final table, and then we're going to arrange by country and year. So this is what it's going to look like, right? So now the type is only cases. That's what we grab, right? The count has been renamed cases here, and then it's sorted first by country and then by year. So the 1999 is prior to the 2000s, right? So we need to make the exact same table for the population now. So same thing, all population now, population in its old column. The count has been renamed population. And now that we have those two, right, we need to combine them into a new data frame, right, that has the cases and the population as columns. So let us do that. I'll show you, keep that there. Oh, okay. Sorry. I did not split this into two operations. So this is actually like the final table that we want. And so essentially what this is doing is we'll go through this, a new table called table 2 cases per cap, right? So you want a table, and then you're grabbing this year column, right? From it wouldn't have mattered. It wouldn't have mattered if you got it from here or from this table. And then you're getting countries from either of the two, and then cases is coming from case, right? This, and population is coming from the other table, this population thing. And then it's passing passing it on to mutate, and then you create this new column, cases per cap, that is just the cases and population. Cases divided by population times 10,000. And then again, we're selecting only the 3 columns. That's why we're not seeing the other 2 columns that we merged into the previous table. Okay. So now we want to add the new rows that we've created back to the original table 2. And in this case, we're taking our table 2 cases per cap, right? And then we're creating this new type column called cases per cap. And then we're renaming in the count cases per cap. So it's usually the new name and then the old name. All right, so now we want to put all of this back into the appropriate place, meaning we want to bind it back into table 2. And bind rows actually stacks one data frame on top of the other one, right? So we had one that had 6 columns, 6 rows, and then the other table has 12 rows, so that's 18 rows. And so that's what we want to see. And then we're again arranging by country, year, type, and count. Okay, so that's looking pretty good. And also note that after we add the cases per cap rows, right? So these guys, the type of count is not coerced to numeric double, right? Because cases per cap is not an integer. All righty, okay. So now let's work with table 4. And let me remind us what table 4 looked like. So these are the 2 tables that have the values, right, in separate columns by year. So this is the cases, and this is the population. Okay, so to work with this table, we need to create a new table, 4C, right? For cases per capita, we want the countries in rows and the years in columns. And so table 4C, again, make a table, right? The country, again, is coming from either of the 2 other tables. And then here you're specifying a new column. Well, let me see. Let's see what this does. Okay. Yeah. So what it's doing is you have a new column called 1999, right? That is now the rate for that. So you're dividing the values of the cases. So column this one, right, by this one. And then the same for the year 2000, right? This was very curious to me. I think I've seen the double brackets, but can anyone remind me like what these double brackets way of, like selecting columns, like what package that's from?
Oh, that is base R.
Oh, that's base R. Okay.
Yeah, that's the way you had to do it. I mean, you still have to do it sometimes, but it's the yeah, that's how you subset anything in base R. Double brackets is to get a single value, like a single thing, and single bracket gets or the whole thing usually. That's not very clear in this case, so never mind that I said that, but it's subsetting down to the column with that name, basically.
I see. And it wouldn't matter if it's, like numeric, why it's in double quotes, like even a string column name would be in double quotes.
Right. The name of the column is always a string. The type of column. So even that's why you have to put the 1999 in the ticks, is because it needs to see it as a name, not as the number 1999.
Got it. Okay. I feel like I'm not used to that syntax. And so when I had tried it this way, right, just saying table 4A and then column 1999, of course, it gives you an error. Yep. And I think Lucy went over this in her lesson, where if you have non-syntactic names, so that are either integers or, starting with an underscore, remember to put in the backticks like this. So this is what I was testing with the backticks, and obviously that works. Okay, sorry for that little digression, but
that
I found that interesting.
If you have column names that have a space in them, you need the backticks around that as well, because it will see the space as like a break in your code. And so basically the backticks let you use names that you shouldn't use is kind of what it comes down to. Got it.
Okay. Yep. So for example, if a column name ended in a parentheses, because sometimes you have like kilograms parentheses or something like that, then you would also need this either backticks or, Yep. That actually helps a lot. Okay, so now in this resulting table, we have our 3 countries. And then now we have the rates by years in columns, right? So the takeaway from this part of the exercise is just the ideal data frame, right, for computing cases per capita is one where you have cases and populations in 2 separate columns, right, which is a tidy data frame. And then you can just create a new column, cases per cap, that is 1 divided by the other, whatever mathematical manipulation you want to make, right? So does anyone have any questions on that section as to what tidy data is and why it's easier to work with it?
I think it's interesting that he has those exercises there, because like the rest of this chapter and a lot of the next chapter is about like how the tidyverse makes all of what we just did a lot easier. So even cleaning up those columns, like there are functions that'll just let you do it. Like you could just take the 2 tables and merge them together, and you don't have to do all this subsetting and complicated work. And it's kind of funny, having more experience with it. I see all that and I'm like, wait, why are they? Oh, right, because they haven't introduced that yet. Okay, it's like, why are they having you do it this way? So. Yes.
But you know what, like for me, this was really great because I feel like that's exactly in a sense like how I work with things. Like, I'm creating a whole bunch of other things that have the things that I want and then putting them together. And so I think that just going through, the nitty gritty of the exercises and how you create all of these things. And I think I feel like I'm still only just getting like a gut level feeling for it, but it was very helpful.
Well, this stuff that's coming up right now with the pivoting, it's really hard for people to grasp, for sure. Yes. That they just renamed all the functions to try to make it clearer, and it still doesn't get through to a lot of people.
Yes. So I've been through this this lesson maybe a couple times, and I'm just like, okay, I think I understand what it's doing. But if the data set gets a little bit more complicated, then I'm like, okay, I think I lost it again. Okay, so let's go on to pivoting then, if no one has any questions. So isn't most data tidy? And the answer is no. So most data that you will encounter, and I'm sure that you guys have already encountered, is going to be untidy. And that is because most people aren't familiar, right, with the principles of tidy data. And it really is hard to derive them yourself unless you've seen this a lot and you've worked with it, right? And then also data is often organized to facilitate something other than the analysis, right? So for example, you organize it to make data entry possible, or whatever it is that you need. I come from the Excel world, and everyone just organizes things however they want, in a sense. So you will generally need some kind of tidying before analysis. Okay, so let's remind ourselves again, this is tidy data. All your variables are in columns. your observations in rows, and then the values are there at the intersection, right? Okay, so what are the steps for tidying data? First of all, you need to figure out what the variables are and what are the observations, right? Sometimes this is very self-explanatory, but other times you're going to have to consult the person that, you know, originally generated data, like what do these columns, rows, and things mean? And then Hadley says you have to resolve one of two common problems. One variable might be spread across many columns, or an observation may be scattered across many rows, right? So say the country is just here, and then whatever was the observation, you could have it in multiple rows and not all together. And then he says, usually it's one or the other, right? A or B, but not both. And that's what I'm still trying to get a sense of. Maybe when I work with many more data sets, I will. So to fix this, he says, these two functions, pivot longer or pivot wider, are like one of like the most basic things that you can do. So let's start with pivot longer, right? So a very common problem is a data set where some of the column names are not names of a variable, but the values of a variable. Okay, so remember our table 4A. And so the values that are listed in columns 1999 and 2000 represent the number of cases of tuberculosis for that country, right? And so again, remember, we want to create the following visualization, right? Which each line represents a country, years on the x-axis. Let's see what that looks like, right? And you have cases on the y-axis, right? And you automatically want this legend to be generated. Okay, so let's go through this. How do we fix that data so that we can make this plotting easy? Let me just scroll here. Okay. So to tidy this, we need to pivot, that's what the function is called, the offending columns into a new pair of variables, so new columns. And we essentially need three parameters, right? The set of columns whose names are values, not variables. So in this example is the 1999 and the 2000. The name of the variable to move the column names to, which is year, because these are years, right? The name of the variable to move the column values to, right? These are cases of TB. And together, those parameters will generate the call to pivot longer. Okay. So let's see what, yeah.
One thing he doesn't really stress here, but it's the rule that we're really fixing is the one observation per row. Because right now, we've got two observations in each row. The Afghanistan row has an observation for 1999 and an observation for 2000. And so pivot longer is when you want to pull those apart into multiple rows so that all the observations, or so that each row is one observation. Does that make sense? And so, like, you know, and there are cases where you can think of a country as an observation, maybe, like that can make sense for certain types of analysis. But for what we're trying to do, we want an observation for 1999. You know, one point is Afghanistan in 1999 and another point is Afghanistan in 2000. So those are different observations.
Yeah,
And so that's where pivot longer comes in, is when you want to pull one observation apart into multiple observations. Does that make sense?
That makes a lot of sense. Yes, thank you. Thank you for the clarification. Okay, I put it there in my notes. So let's see what the call does. So we're taking table 4A and then we do pivot longer, right? The columns, I'm sorry, you can't really see it. Let me just do this again. Table 4A. Oh, no, it's not displaying. Oh, anyway, okay. So essentially the columns 1999 and 2000, right? Yeah.
If you put the double column after table 4A, you the markdown displays both things. The table.
If I put the double column.
Yeah. at
If
the
I
end
put
of
it after?
I think you just have to hit the play button to get the whole
This
box
one?
at once. Yeah, because you were
Yeah, I just
running them one
wanted
at a
them
time. Yeah.
one on top of the other. Yeah, but okay.
Okay. I see what you're saying.
Let's go for this. Yeah. So, okay, just keep that in mind. These are the columns that we're moving to, right? This new column year, and there are the values. So the names of the two columns, 1999, 2000, have gone here, right? And the values for these two columns are now under cases, right? Okay. So just notes that the columns to pivot are specified with this dplyr select style notation, right? So here there are only two columns, 1999 and 2000. So we're listing them individually. And again, note that these are non-syntactic names, right? Because they don't start with a letter and or other conventions. And so they do get surrounded in backticks. The year and cases, the new columns, don't exist in table 4A, right? So the names go in quotes. And in the final result, the pivoted columns are dropped, right? And we get new year and case columns. And then otherwise, all of the relationships between the original variables are preserved, right? Okay, so keep that in mind. And this is a nice graphic to illustrate what has happened, right? So we're starting off with this data frame on the left. These columns have now gone into year, and the column names have become values under this new column. And then the values that were listed for each of these are now in rows for each year. Okay, so pivot longer makes a data set longer, right? Now it looks longer by increasing the number of rows and decreasing the number of columns in the final result. But there is still one issue, right? So if we look at the variable type for year, it is character, right? And we would expect year to be numeric, and that's what we want because we want to manipulate some numbers to be able to plot this. But it's showing up as character. And why does it do this? And it's essentially because the values in the year variable came from column headings, right? In table 4A. These are column headings. Okay, so then to fix that, you can just add a new step to the pipeline, and you just want to mutate year to parse this variable as an integer. So parse as integer the column year. We do that, and now it's integer. Okay, so now we are good to plot. So we take table 4A, we pivot longer. This is just what we did. You mutate. The year is now integer, and now there's the call to ggplot, right? Your aesthetics are, let's just see the example. Year on the x-axis, cases on the y, right? And we're plotting a geom line per country, and then you can specify your pretty colors. And then the geom point aesthetic, you're coloring by country and also giving different, I don't know what these are called, like PCH, different shapes, again by country. So just give different colors and shapes to the different countries, right? And I don't understand this. So scale x continuous, meaning, okay, so this is a continuous scale on the x-axis, and then it's just putting in points or labels for 1999 and 2000.
It's telling it to like only show those on your axis.
Oh, okay.
So I'm going to show you a trick for when you're debugging something. So
okay.
The first thing is if you type Control-Shift-C or Command-Shift-C, that'll comment out the row that you're on.
Yeah.
So we can do that to get rid of it. So go ahead and do that. And then, but if you just run this now, it's going to fail. So what you can always do in a ggplot, see, it's going to give you an error because it's got a plus at the end. So if you just make a new row, new line, and type null, N-U-L-L, all caps. Sorry, all caps. And yeah, the autocorrect was trying to. So if you add null onto a ggplot, it's saying, yeah, never mind, don't add anything. So you can just throw a null at the end of your ggplots, and while you're debugging them, you can turn off different rows, turn them on, and it'll still work. So if you run this now, it does it.
Yeah. Okay.
And so that shows you what that scale is doing.
Yeah.
Don't treat it like a number is basically what you're, don't treat it like you would a normal numeric axis. I only care about 1999 and 2000.
Yeah.
And so that's a good trick, when you're trying to understand what a plot's doing, just go through and turn things on and off and see what happens.
Well, this is great. Yeah. Okay.
But yeah, that null is necessary so that you can turn off the last row without breaking things. And it's a useful way to kind of play with things. It's also useful to know that, like, if you want to add, like, when I first learned about it, was someone at work wanted to add wanted to add an aesthetic conditionally, and we'll learn about that kind of thing later. And so they said, if this condition is true, add this aesthetic. If it's not true, they were like, what do I do if it's not true to make it not break? And they would say, okay, add null if it's not true. And sorry, not this aesthetic, this geom. They wanted to add a geom if the condition was true, and they just added null if the condition's not true, which works because null just doesn't do anything. If you add null to the plot, it doesn't make any difference.
Actually,
this is great. Yeah. As opposed
to
yeah. Go for it.
Yeah, actually, for the visualization purposes, maybe especially for the ear as an x-axis, maybe there is for me, I usually do the two ways. One is I just making the ear as a factor variable. So maybe you can say x equal is factor parenthesis ear. That actually just kind of labeling the ear. Or maybe you can say that scale x, not the continuous, scale x discrete. Discrete means that you just only get the interval by the one incremental kind of interval, not the continuous. The reason why you can get the kind of some kind of a several decimal when you try to do the null by using the continuous, that is because of your ear can be treated as a continuous variable. But if you just say the discrete and then create the breaks, you just say about the treating that one as a kind of integer with the interval with the one or whatever you can break. You can define the steps like 10 steps or 10 incremental or 20 increment, etc. Because you just only have a kind of right now you only have a 2 time period, but if you have 20 years or maybe by quarter, by month, or by day, actually those kind of labeling problem gonna be very messy because it's too many labels. So you have to thinking about how you can abbreviate or make it more like a summarize those kind of things in the visualization purposes.
Right. Yeah, that makes sense. Okay, I'll just leave that there. Okay, anyone have any questions or comment?
Probably go ahead and uncomment the scale x continuous just so you get back to the plot that you started with. So, and yeah, you can delete it, or you can always Control-Shift-C. So there we go. Back to the plot you started with.
Perfect. Okay. I don't know what this is. Oh, that must be the same figure. Okay. So we went through one example. So now we want to pivot longer to tidy table 4b in a similar fashion. So I think this is just exactly the same, right? Yeah, instead of cases, this is population, right? And now we want to combine the tidied versions of table 4a and 4b into a single table. And we need to use dplyr left join. And we will learn more about this in a future chapter. So we have tidied 4a, right? Tidied 4b, and then you want to left join. So the left join just means it's going to merge two data frames, and the merge will return all rows on the left table, right? And any rows that match from the second table. It says a left join and R will not return values of the second table which do not already exist in the first table. All right, so okay, so now that looks much better. Looks like table 1, which was the tidy one, and that's what we want, right? Okay, so let's go on to the second function. So pivot wider is the opposite of pivot longer, as you may guess by the name, right? And so you use it when an observation is scattered across multiple rows. So let's take table 2, and an observation is in a country in a year, but each observation is spread across 2 rows. Yes, because now you have cases in population. Wait, is that what is meaning?
Yes.
Yes, yes. I was just making sure that it wasn't referring to the years. Okay, all right. So as in the previous example, we want the rate, right, is each of the cases divided by the population for each country in a given year, and to put that in a new column like so. Here's the rate. So what do we need, right? So we need, again, a data frame with cases and population as separate columns. In those columns, each cell will hold the values of the relevant counts, right? So let's analyze this similarly to what we did with the pivot longer. But in this case, we only need 2 parameters. The column to take the variable names from, so the type, and the column to take the values from, and that's the count column. So let's see, pivot wider. So there's table 2 again. And now we're gonna take the names from type, cases and population, and the values from count. That's the number of cases, that's the population. And yeah, so this is what it's gonna look like, right? Now you have cases and population in 2 separate columns. And just graphically, this is what has happened. Cases has gone into this column, population into this column, and it's taking the values from the count column in the original table. Okay, so now that we have the data in this wider format, we can create the data frame that motivated this tidy example. Okay, that's the new tidy one. And I think what he's doing here is just exactly the same, right? So we send this visualization, and now it's easier to be able to plot it, other than we used to have cases here, but now it's the rate and year on the x-axis. Okay, so let's go one step further now, and we want to widen the data to record cases, population, and rate for 1999 and 2000 in separate columns, such as the following. So let's see why we're doing this. Okay, so now you want the cases for 1999 with the values, and then population, so each thing by year, okay? So okay, this representation is one, rarely useful for data analysis, and 2, it might be useful as the basis for a table for communication of results in a data analysis report. Yeah, that makes sense. Okay. To achieve these, we need to add year information in the column headings, right? Yeah. For cases, population, and rate, and then distribute the values that are currently under these 3 columns into 6 new columns. Okay, yeah, that makes sense. 2 columns for each year that we have data for. And so this is what's happening, right? Yeah. Okay, so to do this, we're going to take advantage of the fact that the pivot functions can operate on multiple columns at once. So the first 3 lines of the following code chunk is what we've already done in the previous step. Yep, let's see that. So, okay, and then you create this new column rate. That makes sense. Okay, and now we add another pivot wider step where the values for the added columns from cases, population, and rate, and the column names are automatically suffixed with values from the year variable. All right. So this is the second pivot wider. The names are coming from year and the values from cases, population, and rate. Okay. Well, that's interesting. Okay, and I guess this will always do this suffixing automatically. That's actually good to know. Okay, and then the last step is to relocate columns in the resulting data frame. So the columns from 1999 come before those from 2000. And so you can use this function relocate to move all of the 1999 columns ahead of the 2000 columns. Like so, okay. And essentially relocate, you can just use this to change column positions, same syntax as select, and you can just, it's easy to move column blocks, you know, from different positions. That was actually really useful to know. This is the link in case you guys want more information on that specific function. And this was just for me, I was just playing around with seeing exactly what you could relocate, and you can do all sorts of fancy things, right? If you want, like, for example, like all of your columns starting with A after C, or all sorts of different conditions. Okay, so as you might have guessed from their names, pivot wider and pivot longer are complements, right? Pivot longer makes wide tables narrower and longer, and pivot wider makes long tables shorter and wider. Okay. Okay, so let's go on to the exercise. It says, why are pivot longer and pivot wider not perfectly symmetrical? Okay, so here we have a table called stocks with a year column. I'm not exactly sure what this is, and then the returns for the year. You have 2 years, 2015 and 2016.
It's just the first half of the year.
First half of the year. Okay.
Yep.
Sounds good. Okay. So now if we take this and we pivot wider, right? The names are coming from year. So now it's splitting it into 2 columns, and the values are coming from return. Okay.
I just want to say, like, he should use examples that have more than 2 things, because wider and longer don't make sense until you have at least 3, because it keeps the same number of columns in like every example he uses.
Yes, yes.
If there were 3 years, then the table would actually get wider when you pivot wider. But since there are only 2 years, it stays the same width.
Yeah, that is true. Yeah,
yeah.
Maybe a suggestion for future iterations of the, you know, the book. I don't know how much he wants to work on that, but
they've worked on. It's interesting because when the book was published, these functions were different, and they were spread and gather, and people were confused by the names, so they renamed them and they updated the book to match all the new functions. So, so they do work on it, and so I don't know. I might point that out. Of these examples don't really make, you know, it's not obvious what it means because it's not really getting wider.
Yeah. You know, I think that pivot wider and pivot longer are improvements over, you know, spread and gather, but I feel like it still doesn't properly give a sense of what it's trying to do. Like it's slightly ambiguous or confusing.
Yeah, he worked really hard on that, and it's still not perfect, but it's like,
I'm sure.
I don't know what to do that would be better without the function names being just insanely long. Like
insanely long. No, exactly. Yeah.
Spread observations over a wider table.
Exactly. Yeah.
Anyway.
Actually, the pivot wider and pivot longer before this function is developed, there is a package called the reshape and reshape 2 packages in R.
Yeah.
And then there is a function called melt and cast to transforming longer to wider, wider to longer. And also what I understand, because when I wrangling the some kind of a large data set, especially
Mm-hmm.
for the time series data set like this example. We actually, most of our analysis packages supports the longer format rather than the wider format.
Yeah.
Because like for example, like when you have like a 10-month time series economic growth data set,
Mm-hmm.
that actually I prefer to use the longer format, because that means you need to get the separate time column to as a variable for the analysis. And also, in case of the wider function is mostly useful when you have a cross-sectional. That means you have observation data at the one specific time point. In that case, pivot wider works very well, because you have to separate the independent columns for the analysis. Do you understand? Does that make sense? Because pivot longer is very useful, actually, especially for me, when that I have a lot of a time series data set, like 10 months or sometimes 30 years, 40 years data sets about the economic growth or downturn kind of a data by the country or by the city, etc. In that case, most of the R packages usually usually takes the longer format rather than the wider format.
Okay. I see. Yeah. I think, it's probably like I shouldn't be complaining about function names at this stage of my R learning, because I think that, it'll come the more you just work with this and get a feel for it.
Well, and so, I do think it would be helpful if he just gave one more column or one more set. So like if you had the stocks went to 2017 as well, I think it's a lot more obvious that, okay, that now it's getting wider when you merge them together.
Right. Yes, I totally agree with that.
And I would say like Reshape and Reshape 2 are direct ancestors of tidyr. Like those are Hadley's older packages. So if you can avoid them, I recommend avoiding them, because they became tidyr. Now you might see some old code that uses them, but you shouldn't need to use them anymore. Like if you go to the documentation of them, they say I'm only making updates to this to keep it on CRAN for old projects. Please don't use it. So.
Oh, I see. Yeah.
But you will find some people who are like, well, I know how to do it in Reshape 2, so I'm going to do it in Reshape 2 forever. And more power to you if that's how you work. Right.
That makes sense. Okay, so what had we done? We had pivoted wider, right? Now we have, 2 columns per year with the returns in there. Okay, so now take this and we'll pivot it longer. And we're taking the names of the columns, these 2, right? Put in a new column year with the quotes, right? Because year doesn't exist in pivot wider data frame, and then take the values. All right, so let's compare that to the original stocks. So same columns, half year and return, but something's different. So look at the variable types and think about the column names, right? So the reason why these 2 functions are not perfectly symmetrical, right, is in a sense here in our, after you pivot wider and pivot longer, year has become character, and the original stocks has year as a double. And what is happening is the column type information is lost when the data frame is converted from wide to long. So pivot longer stacks multiple columns, right? And they may have had multiple data types into a single column with a single data type. And so this transformation essentially just throws away the individual data types of the original column. And this character type is used as a default. So that's a safe assumption, right? Since syntactically valid column names can only be character, that makes sense. And then pivot wider creates column names from the values in a column. So the values could be numbers like years, but the values will all have the same type. So pivot wider can preserve this when it creates new columns, right? So if the original variable used to create the column names did not have a character data type, then like the round trip is not going to reproduce the same data set. Okay, yeah, that makes sense. But okay, I had, let's see. So what was the question that I had here? Okay, the pivot wider names came from column and the returns. Okay, but so if you just do this part, right, the pivot wider, you take stocks, the names from year and values from the return, the column types at this stage are preserved, right? So I'm not exactly sure, yeah, what he means by stored.
Specifically, it's the 2015 and 2016 are
right,
like the names. The name 2015 isn't a number anymore. It's a column name, which technically is its own data type, but when it comes back, it's going to be character. And so until
the column name, right, not the column type. Okay.
Right. Yeah.
Yeah, I see. Yeah. Okay. Because, then just ignore my second column, because I was like, if it's preserving it at this point and they're doubles, why not just preserve it once you do the pivot longer? But got it. Okay, yeah, ignore this. John just answered that. Okay. So an additional question for this exercise was the pivot longer has a names ptype argument. Names ptype equals list year double. What does it do? So in the current version of tidyr, the names ptype argument does not convert the year column to a numeric vector, and it will raise an error. So I think this was a little old in that it's for previous versions, right? So you need to use the names transform argument to pivot longer, which provides a function to coerce the column to a different data type. So names transforms list year as numeric, right? So now it's double instead of character. Yeah.
That's funny. Like you could probably figure out roughly when they made the edits to the book, because like, the pivot functions existed, but not names transform. And they were still kind of in the process of making things make sense.
Yeah, I wasn't sure why they wanted us to look into this names p-type argument when it actually doesn't do anything in this version.
Right.
So that is why. And I made a little note about this names p-type. Names p-type is a list of column name prototypes, right? So a prototype or p-type is a zero-length vector, like integer, numeric, defines the type, class, and attributes of the vector. But you don't need to remember that. Just remember to transform to whatever type you want. Okay, so on to exercise.
And just before we move on, and technically you should do names transform as integer probably, because you don't need decimal places on the years. And so this is, I came into R through working in databases first, and like for storage, it kind of matters whether you call it a double or an integer, or numeric or integer, because you need a lot more memory to store a double than you do an integer. You need to have room in RAM in case it has a decimal point, basically. A lot of times what you're doing, it won't matter, but I noticed these things that, well, 2015, that's an integer. Don't store it as a double, because that's kind of wasteful. It's basically my way of looking at it. And so that would be,
yeah.
Like technically you should do as integer on that. And it is useful. I had this discussion with someone once, because we were like, some column was logical, and they were like, but what's the difference? Why does it matter whether you store that as logical or as zeros and ones?
Yeah.
And it's like, it tells you more about the data if you have it in the proper data type. So sure, as you can think of a 0 as false and a 1 as true, but if a 0 is actually false and the word false and a 1's the word true, then you know that that's what's supposed to be there. And if you add a 2, technically 2 would register as true, but you're being weird at that point, and it like tells you more about it. So I think I'm more kind of more a stickler for these kinds of things than a lot of people, but I try to make sure that the data types are really what the data is, so that it's really clear as I'm working for it on it in the future, that, you know, if I say that it's an integer and I get an error, I can't convert to a, you know, 2015.5 to an integer. That tells me, wait, why is there 2015.5 in that column? I didn't expect that to be there, yada, yada, yada. So like,
Right. Okay, but so
yeah.
in that case, right, if you have year as int, remember the very first ggplot where the x-axis was continuous?
Right.
You wouldn't be able to specify that as continuous, right? That would be discrete if it's because it's going to go 2015, 2016, 2017.
It still will, because R is pretty, and this is why it's not that really that big of a deal, is R is pretty lax about switching things back and forth between integers and double. It's like, oh, you wanted it, okay, you're treating it like a double, I'll just make it a double. So that's, I don't know, this is probably a tangent that most people will never care about, but it is something, I don't know, I have had some cases where it has saved me because something comes up, you know, I get an error message that I wouldn't have gotten if I just treated it like a double, and it tells me, oh, something's weird with that column. Or, you know, technically, you know, you could just leave it as character, technically, because if you're just alphabetizing 2015, 2016, those are going to be alphabetized in the proper order. It would be fine, but you take the time to convert it to an integer or to a double, either way. And because that tells you, if you have a year of B, you're like, oh, something's wrong with that row. I'm reading it in wrong. Something's wrong. And so, you know, the more you can get it to what it really is, I mean, technically treating it as an actual year from like a time package, like it's not really just an integer, it's a year, and it should have certain properties because it's a year.
No,
that would also
that
be
actually
useful.
Makes a lot of sense, right? Because at some point, like you were saying, it could convert it to some kind of decimal thing, and then that absolutely makes no sense,
right?
Unless you wanted it that way to display parts of a year, but
right,
you know, that's usually not conventional. So, yeah.
Okay. And so I do find that just kind of when you're working with data, the more you can do to kind of put in the data what you know about the data. Like I have validated that these are all integers, so I'm going to call them integers. And that way, the next time I'm looking at the data, I don't have to think, oh, are there any in there that are weird? Nope, because it's an integer, so they all must be integers. Yeah.
That makes sense. Okay, so next exercise, why does this code fail? So let's see, why does it fail? And it does fail. Okay, table 4A, what's the problem? So we're trying to pivot longer, column names to year and values to cases. And what is the code? Okay, because the column names, as we've already been over, are non-syntactic variable names, right? So syntactic name, it consists of letters, digits, underscores, and periods. Can't begin with that's just an underscore. I think it just put these, you know, next line things, or digit, and can't use reserved words like true, null, if, function, for example, right? You can also see question mark reserved for more reserved names. When selecting variables, so the columns from a data frame, tidyverse will interpret numbers, right, as column numbers. So in this case, pivot longer tries to select the 1999 and 2000 columns of the data set. So we only have 3, and obviously these do not exist. So to select the columns 1999 and 2000, the names must be surrounded in backticks or provided as strings. So here's the backticks, or as John had explained, you know, the quotes as strings. And so these should work. Yeah, that was actually really interesting as to how it interprets those as positions or names of columns in a certain position. Let me just check the time. So yeah, we're definitely not getting through all of this today because there's still a whole section on separating and uniting, and then, you know, some extra things at the end. So let's see, I
was going to say, if we can kind of, you know, wrap up
what
you're looking at, and then yeah, we'll just continue next week with the rest of chapter 12.
Okay. Are you guys interested in going over all of the exercises, or, is that too much? Because I can definitely streamline it for next time.
I think it's really nice to do it, but it does take a lot more time that way.
Yeah, so I myself found it super helpful because I really like to take my time and analyze what's happening, what moved where, and to get to know the syntax. But if it's too basic for some people, or you don't want to go over it, then I can just take out most of the exercise for next time, and we just go over
so
the main.
There are a couple of comments that are, let's try to pick out important exercises or
Okay.
exemplar exercises next time,
Yeah.
and we'll go through that way instead of going through everyone. That makes sense to me too. But I mean, the exercises are, I think it's more important to go through the exercises than the other parts of the book, really. They really put it all together and drill in. So the more, maybe cut out a little bit of the build up to the exercises.
Okay. Let me just make
Actually,
notes for
true.
myself.
I kind of agree with you, John. I wish we would have just do the exercises and then people would probably, I don't know, refer to the book for in a situation where, maybe additional information is needed, but I don't know. I don't know if that would work. That would be my style, really, if I want to really understand how to do most of this, because the exercises are designed in such a way that you kind of go back and forth with past chapters that you have read. So you get a chance to implement the skills that you've learned along the way up to that point.
Okay.
All right.
So I will try and do that for next time. So just give less introduction on what the functions do, and then pick out some of the exercises, because there were quite a few. Okay, so exercise 3 then. What would happen if you widen this table, right? Why? And how could you add a new column to uniquely identify each value? Okay. So what do we want to widen this? Oh, because in this column key, you have age, height, right? So if you widen it, let's see what happens. Yeah, so missing values, you don't have unique things. Yes, okay. Interesting. So what is it doing here is actually making columns that are lists of vectors, right? Because the name and key columns do not uniquely identify the rows. And you have 2 rows with values for the age of Philip Woods. Yes, correct. Okay. So widening this data frame using pivot wider produces, we want to solve the problem by adding a row with a distinct observation count for each combination of the name and key. So let's see what it's doing here. People you group by name. Let me see, name, where's the name and key? Name and key, got it, okay. And now you create a new column that has the observation, which is equal to the row number. Is that correct?
Yeah, so it's saying, go ahead and scroll down.
Yeah.
If you look at row 1 and row 3, those are the same name and key. So that's the first instance of that and the second instance of that. Does that make sense?
Got it. Yeah. So this is first instance, and then exactly. The second is it's doing a count of the instances. Got it. Okay. So now we can make people 2 wider because the combination of names and observations. So this and this will uniquely identify the rows in this wider data frame, right? So now you have what you wanted. This is age. This is the first observation for Philip Woods. And here is the second observation for Philip Woods, instead of getting those lists. Okay, we can also solve this problem by keeping only distinct rows of the name and key values and just drop the duplicate rows, right? So now Philip Woods, we've only kept his age at 45 and not the age at 50, which we had before, right? But my question here is, why would you just arbitrarily drop age 50, right, for this person, and keep this age 45? And so, in fact, Hadley mentions this, and he says, before dropping any rows, you need to understand why there are duplicates in the data, right? So the duplicate values may not just be a nuisance, but may indicate deeper problems with this data. Okay, I think why don't we stop there? Because this example I think was similar to, only just using, like counts, and then we can just pick it up next time, and I'll try and cull the exercises so that it's less. so we're not here all day.
Yes, I think everyone's in agreement that
okay, that sounds good.
Like, don't cut too much. It was great. It was really nice to really dive into stuff. And like I said, these pivots, like every once in a while there's a flare up on like our stats Twitter of someone decides they have the best way to do it, but then it's like, oh wait, but that doesn't work for the, so
right. Yeah.
I think pivot wider and pivot longer are easier to understand than gather and spread, or spread and gather, I guess, to put them in the right order. It does really amuse me though that all the examples had 2, and so it like didn't get wider and it didn't get longer until you actually like look at it, whatever. So
yeah.
So we I don't know, make sure to like kind of look at examples like that stocks one. You can just put in another year and you can see how it gets longer and wider, longer versus wider. But yeah, all right, we will pick up on chapter 12 next week.
Yeah, we'll go on to separating and uniting then next time.
Excellent.
Okay, sounds good.
Bye.